this morning is Roberto Percacci, talking about renormalization group and scattering in a shift-invariant scalar model. Thank you.
Thanks. Thanks to the organizer for inviting me here. The general theme of my talk is going to be the comparison between different flavors of renormalization group. And I'm going to talk mostly about, actually entirely, about renormalization group applied to particle physics. There's another story with application to condensed matter physics, and I don't have much to say about that. But of course, particle physics is one domain where RG has important applications. And when particle physicists talk about running couplings, they mean the following. They define the coupling in terms of some scattering amplitude. The scattering amplitude is in some particular kinematical configurations characterized by a momentum scale P. You fix the momentum scale P and you define the coupling at that scale. You call this a renormalization scale, mu r, let's call it. And then what they call running, and I will call it in this talk physical running, is the dependence of the coupling on this renormalization scale. So that's one concept. In perturbation theory, and this is a very physical definition. In perturbation theory, you need to introduce in calculations a scale mu in order to fix dimensions. For example, in dimensional regularization, or when you use cutoff, you have logs of momentum, for example, and then you need a momentum divided. You need to divide it by some scale mu. So the dependence of the coupling on this parameter mu, I will call mu running. It's a different thing from mu r. And then in a non-perturbative context, one can define a renormalization group as the dependence of the couplings in the effective action on some cutoff. For example, ultraviolet cutoff in Wilson's definition, or infrared cutoff in what we call the FRG, the Functional Renormalization Group. So these are all different definitions of RG, and the question that I will ask is, when do they agree in sometimes, and sometimes they don't. And I'm going to discuss this question in the context of this very simple scalar model, which has two kinetic terms, a normal kinetic term and a high derivative one, and then an interaction with 4 fields and 4 derivatives. And the main feature of this action is that it is invariant under shifts of the field. So phi goes into phi plus constant is a symmetry of this theory. So the analysis of the running of the couplings of this model using the FRG was done in a paper in collaboration with Diego Bucho, one of my students. It's already published. And then the analysis of the physical running in this model, which is something ongoing. It's going to appear soon. It's collaboration with John Donoghue. And I will first, in my talk, I will first motivate why I study this model. Motivation comes mainly from gravity, actually. That's how I arrived at it. I will then talk about the study of this model with the FRG, and then in the third part about scatterings. Some of you have already heard part of this, but there are some new results in the third part. And I should say that this is a case where we go not from perturbative to non-perturbative, but it's the opposite. We studied the non-perturbative situation first, and then we realized that in order to understand the physics, it's better to check what happens in the perturbative situation. That's the history of this, of how we got to that. Okay, so the motivation for gravity is that there are theories of gravity with terms with 4 derivatives. So in this, here you see you have an action for gravity with the cosmological term, the Hilbert term, which has two derivatives, and then four derivative terms, quadratic in curvatures. So C squared is Weil tensor squared, R is a curvature scalar, and E is a Gauss-Bonnet term, so it's topological. You can ignore it to some extent. So this theory was proven by Kelly-Stell long ago to be renormalizable, which is good. The problem is that being a theory with four derivatives, it has ghosts, and that's why it was not widely accepted as a good theory for quantum gravity. The beta functions for this theory, the perturbative beta functions, were computed also long ago by several authors, and Avramidi and Barvinsky were the first to get all the coefficients right. And you see that, so lambda appears here as an overall prefactor of all the high derivative terms. It is the perturbative coupling of the theory, and its beta function is a negative coefficient. So if lambda is positive, then it is asymptotically free. This was an old result, which is good. In some sense, it suggests that gravity may behave like QCD. In QCD, we have asymptotic freedom in the ultraviolet, so the theory is weakly coupled at very high energy, because that's what QCD is like. And at low energy, strong interactions are described by the chiral model of pions, which is a theory which becomes free in the infrared. It's weakly coupled at very low energies. In between, we have this region of strong coupling that in QCD is dealt with by numerical methods. And so the fact that high derivative gravity is asymptotically free suggests that gravity may also have a similar behavior of being weakly coupled at the extremes and strongly coupled somewhere in the middle, perhaps near the Planck scale. Now, another possibility, an alternative to asymptotic freedom, is asymptotic safety, which means that the coupling, instead of going to zero in the UV, they go to some finite limits. And those particular four derivative models, in the context of asymptotic safety, have been used as Ansätze for the coarse-grained effective action. You put that ansatz into the FRG, and you derive beta functions for the couplings. And if you do that at perturbative in a one-loop approximation of the FRG, you just reproduce the perturbative beta functions that I had written earlier. And if you go beyond the one-loop approximation, you get extra terms that have been calculated, for example, in an expansion in the inverse of Newton coupling. So Z is the inverse of Newton coupling. So you see here in an expansion in Z, the beta function of lambda is the one-loop term plus a term which is linear in Z. So you can look at the fixed points of these beta functions. There are several of them, even more than are written here. Perhaps the most important one is the first. This is the one with lambda equal to 0, so it's the one that corresponds to asymptotic freedom. It's a Gaussian fixed point. In spite of the fact that Newton coupling is non-zero here, still it's a Gaussian fixed point, which is made clear by the fact that the scaling exponents at that fixed point are just the canonical dimensions of all the couplings. And then there are some other fixed points. And so in this case, you see that we have two fixed points. The one that corresponds to Einstein theory at low energy. So this describes GR as we know it, describes gravity as we know it. There's a stellar fixed point with four derivatives, which may provide a possible ultraviolet completion. And there seem to be other fixed points, non-trivial ones, which support perhaps asymptotic safety instead. And then there are several questions which are left still unanswered. And perhaps the most important one is, can we actually flow from the between these fixed points. Can we flow from, for example, from one of those non-trivial ones in the ultraviolet to the Einstein-Hilbert fixed point in the infrared? That is very difficult to study in the case of gravity, and that's why at some point I decided to look at a toy model. And the toy model is this scalar, shift-invariant scalar, which has some of the features of GR, of gravity, in the sense that there is the two-derivative kinetic term here, which similar to the Hilbert term. It has two derivatives. There are this four-derivative term, which is analog of the curvature squared terms, and there is an interaction which always involves derivatives, as in gravity. Okay, so that is a sort of very simple, sketchy model, but a model where calculations are much easier. So one may hope to learn something from this. Well, so this theory has two fixed points, two Gaussian fixed points. So if you put the coupling here to 0 and Z2 to 0, you just have this free theory with two derivatives. If you put Z1 and the coupling to 0, you have a free theory with four derivatives. So in the first case, the field has canonical dimension 1. And if the field has dimension 1, then Z2 has dimension of inverse mass squared, and G has dimension of inverse mass to the power 4. So this is a typical non-renormalizable theory from power counting. Okay, and typically people would treat it using effective field theory methods, like the theory of pions in QCD. On the other hand, if you expand around the four-derivative Gaussian fixed point, the field is dimensionless, and so this term actually, this Z1 is a mass, so this looks like a mass term for phi, and G is dimensionless, and so this looks like a renormalizable theory, okay, which is a totally different story apparently. But there must be some matching between them. So we have these 2 points around which we can expand, and with the FIG we can study the flow from one to the other. We can ask the question, can one flow from one to the other? Actually, at the classical level, one can run, and this was already pointed out by Rosten and also by Razvan and Dario in some of their papers. If you put the coupling to 0, and you consider just these two, to say it in a very trivial way, this is the term that dominates in the ultraviolet, and this is the term that dominates in the infrared, and that, in a sense, is you can think of as a RG flow from one Gaussian fixed point to the other. But we were interested in the question of can one have such a flow in the interacting theory, which is a bit more, slightly more complicated. So with the FIG, you can compute the beta functions. They are written here. I won't spend too much time to comment about them. Perhaps the only thing that I want to point out is that Z2 does not run at all in the FIG. Z1 does, and this gives rise to some anomalous dimension called eta1. And well, these are the beta functions of the dimension full couplings. But for the to study the RG, we have to look at dimensionless coupling. We have to multiply dimension full couplings by powers of the cutoff. And now, how we do this depends whether the field is dimension full or dimensionless. So there are two parametrizations. I start with the dimension full field, the dimension of mass. So I define G tilde and Z2 tilde by multiplying with these powers of K. And these are the corresponding beta functions. And they have some fixed points. There's a Gaussian fixed point here, where all the coupling is 0, and the scaling exponents are just the canonical dimensions of the Z2 and G. And then there's a bunch of non-trivial fixed points that we may or may not trust. We may or not believe that they exist really, but anyway, they are there. This is similar to what we see in gravity. And these fixed points have been already noted by some of the authors listed here. If you parameterize in the other parameterization with dimensionless fields, there's a different definition of the dimensionless couplings given here, and different beta functions and different fixed points in principle. So you see, here you have the other fixed point, the high derivative one, where the scaling exponent are 0 and 2. That's, so the coupling is dimensionless, remember, and this corresponds to the mass term. And then there's another fixed point that I call NGFP3, which can be identified with one of those in the previous table, NGFP3 here. Why do I identify them? Because they have the same scaling exponents. You can see, for example, this number 10.84 reappears here. So same scaling exponents means the same fixed point. Now, the relation between these two descriptions is given by a certain transformation. Obviously, we've defined the couplings in a certain way. We know how we define them. We can relate it to definitions. And the relation is given here. And you can think of this as a sort of coordinate transformation on theory space, like having two charts in the sense of manifolds. And then things become a bit clearer by looking at the picture of the flows. So on the left-hand side, we have the chart that comes from the dimension full field. On the right-hand side, the chart where you use a dimensionless field. So let's look at this. There are, well, the beta functions. Well, first of all, here in the middle, in the origin, you have the Gaussian fixed point with two derivatives here. The beta functions have some singularities along these red lines, so we don't want to cross those. The interesting thing happened in the lower right quadrant, where you have this flow, and there is a non-trivial fixed point here. Now, I should say something about what are those axes. So vertical axis is the coupling G tilde, and horizontal axis here is related to Z2. Now, in the other chart, you have the Gaussian fixed point with four derivatives sitting in the middle. So here the coupling is again the axes correspond to the coupling is a horizontal axis, and Z1 some version of Z1, the dimensionless version of Z1 on the horizontal axis. The relation which I wrote earlier is that this axis is the inverse of that one. So Z1 going to infinity correspond to Z tilde 2 goes to 0 and vice versa. So you have an inversion here on the horizontal axis. And the transformation in the vertical axis is a bit more complicated. But you see, in this, if you look at fixed points, for example, in this chart, you see the GFP2, but GFP1 is nowhere to be seen. And the opposite is true in the other chart. So you say, where is the other fixed point? We know that it exists. And the answer is that the other fixed point is at infinity. In this chart, the fixed point with four derivatives sits down here. In this chart, the fixed points with two derivatives corresponds to this whole half line here at infinity. So if you start in the ultraviolet from the theory with four derivatives, you can flow down in the infrared towards the fixed point with two derivatives, which sits here. And this corresponds to trajectories that go from this point to the origin here. Okay, so that's the relation between these two charts. And now there is a couple of features that I should mention here. There are some trajectories which remain perturbative throughout for all scales. You see, if you start here and you go and you switch on G, but infinitesimally, G remains infinitesimal for all Ks, all the way to the infrared. So at some point here, halfway in the flow, you can convert to this other chart, and you end up again with a small g, and you end at in the origin. So you have a theory that is free both in the ultraviolet and in the infrared, and is weakly coupled in the middle. You can have such trajectories. But then there are other trajectories where the theory is strongly coupled in the middle. You see this, the trajectory that goes from this non-trivial fixed point to the Gaussian one at low energy is a limiting case of these trajectories as they become stronger and stronger, more strongly coupled at intermediate scales. And the best thing that happens here is that as I said, here, when you do perturbation theory around this fixed point, the dimension of the field is 0. And in perturbation theory around this fixed point, the dimension of the field is 1. Now, as you flow, there is a zeta that flows too. Now, you can absorb the flow of zeta into the field. You can keep zeta equal to 1 by rescaling the field. But if you do that, the field then becomes scale dependent. You have to rescale the field as you renormalize. And this means that the field does not have dimension, the original dimension, but the original dimension plus an anomalous dimension. And it turns out that the anomalous dimension continuously changes in such a way that it precisely interpolates between 0 and 1 as you flow from this fixed point to that fixed point. So that is very nice, because in general, when you flow between fixed points, you can only calculate these dimensions approximately. And I think because here the fixed points are both free, somewhat you get a nicer situation where the calculation of the dimension actually works exactly. Okay. So this is the story from the FRG. I mentioned quickly some generalization. You can consider fixed points where you have of the type phi box to the k phi. I will call this Gaussian fixed point k. These have been studied in as conformal field theories in this paper. Every one of them defines a perturbative expansion, and we can then define a chart on theory space based on that. So for each of those fixed points, Gaussian fixed points, you can define a chart, and every chart contains only one Gaussian fixed point, and all the others lie in this closure at infinity. And there seem to exist flows between all of them. So if you start from GFP you can flow to GFP K prime as long as K prime is less than K. I have discussed this in the previous slides, the flow from K equal to 2 to K equal to 1. And I want to mention that there's also a familiar story, which is the flow from K equal to 1 to K equal to 0 that you know actually already. So GFP1 is a fixed point with 2 derivatives, the Gaussian fixed point with 2 derivatives. And GFP0 is just the free theory that has only a mass term. So there's no propagation, there's just a mass. You can flow between them with this quartic coupling. This flow, well, for this theory, the beta of lambda goes like lambda square, and then as was already noted by Simanzik many years ago, this theory is asymptotically free in the ultraviolet when lambda is negative, okay? So you see that And so that gives you a flow from the normal Gaussian fixed point at in the ultraviolet to the free theory with only a mass, so no degrees of freedom in the infrared. It's a special case of all that. I should mention that this theory that we studied here, the flow from between these two fixed points is realized only for negative coupling, which is unphysical. Somebody was talking yesterday about negative coupling being unstable. So it is. I'm not saying that this is a good theory. I said this is a case study for renormalization group. Okay, so I'm not advertising it as being a good theory necessarily. All right. So from this FRG study, you could say, well, it's encouraging that there are trajectories from the 4 derivative to the 2 derivative fixed point. And we also see that asymptotic safety can be seen as a limiting case of asymptotic freedom, in the sense that in that phase diagram, there's only one asymptotically safe trajectory, and you can see it as a limit of a one-parameter family of asymptotically free trajectories. Now, you can ask, what is the physics of this theory? What would you see if you did some experiment? Now, of course, if you understand the physics, you need observables. The couplings themselves are not observables. And so in the context of particle physics, we just apply the observables of, we just study the observables of particle physics, which is cross sections and decay rates and so on. So that's why we, at some point, we started to calculate scattering amplitudes. And since I don't know how to calculate scattering amplitudes non-perturbatively, we just did the calculation at one loop. And then to compare the scattering amplitude to the beta functions coming from the FRG, we had, in order to compare apples with apples, we had to downgrade the FRG from whatever it is down to one loop approximation, which is easy. You just forget some terms in the FRG. And I'm not going to repeat that, because the one loop approximation of the FRG has a very similar, qualitatively, very same shape that I showed in the slides earlier. So I don't need to repeat the whole story. All right. Then I'm going to reparameterize here the Lagrangian a little bit. I will write what I called Z2 previously. I write as Z1 divided by m squared. Remember, Z2 had dimension of inverse mass squared. So I want to make this more explicit, that it's an inverse mass. So I introduce this mass m, and I write this term like that. And what I previously called G, I will write now in this way. G, the previous G had dimension of inverse mass to the 4. The new G here is dimensionless, and there's a mass, the mass appears down here. So the theory, this is just to emphasize that this theory has two mass scales. One is the m squared, which is the mass of the ghost. If you consider only these two terms and you look at the propagator, you will see that it propagates a massless scalar and a massive ghost. And the mass of the ghost is m. And then the interaction has another characteristic scale, which is the scale. You see, here you have 4 derivatives. So if you go to momentum space, you have something like momentum to the power 4 multiplied by g divided by m to the 4. So this means that when the momentum here becomes of the order of m divided by 4th root of g, this term becomes large. So you enter into a strongly interacting regime, okay? So if you are at scales below this, you are weakly interacting. Above it, you are strongly interacting. And since we want to have some regime where the ghosts propagate and are weakly coupled, we're going to assume that G is small, so that this strong interaction scale is larger or much larger than the mass of the ghost. Okay, so then we have to distinguish these three different energy domains. If the energy is less than m, we are in the low energy regime, where only the massless particles propagate, and they are weakly coupled. And the massive ghosts cannot be excited because you are below the threshold for production of massive particles. Then there is an intermediate scale where the ghosts also propagate, but they are still weakly coupled. And then there is a high energy regime where apparently you enter into a strongly interacting phase. We don't fully understand that, what happens there. So we'll mostly talk about the first two regimes. Now, let's start by looking at the two-point function. The one-loop correction to the two-point function has a divergent part, so we're using here dimensional regularization. You see that it is proportional to p square. So it means that we have to renormalize Z1. There is nothing containing p to the power 4, so we don't need to renormalize Z2. And this is consistent with the FRG, where I told you that Z2 does not run. So you have to renormalize Z1, but, you see there is a term here which goes like the log of m square over mu square. And if you take the derivative of this with respect to mu, you will get a beta function for Z1. This is what I called mu running in my first slide. But you see that this mu running actually, it says nothing about the momentum dependence of the two-point function. The momentum dependence is always p square. So when you renormalize and you fix this Z1 at a particular scale, particular momentum p, it remains the same at any other momentum. So this mu dependence tells us nothing about the momentum dependence of the two-point function. So it's not physical running in that sense. The physical beta function of Z1 is 0 because there's just p square, full stop. Okay, so there is mu running of Z1, but no physical running. Now let's look at the 4-point function. And we start by considering it in the low energy regime. So in low energy, even without knowing about what happens at higher energy, this looks like a non-renormalizable theory, as I said, so you can treat it using effective field theory methods. At low energy, the two derivative part of the propagator dominates over the four derivative part. So let's forget the four derivative part altogether. And then you would just write an effective Lagrangian that contains the two derivative propagator, the interaction with four derivatives that we had before, and then you could add terms with 6 and 8 derivatives with these particular forms here, and even higher if you wanted. If you now do one loop calculation in the effective field theory, you have to renormalize G. And this is the form of the renormalized G in terms of the bare one. Once again, as in the case of the two-point function, there's this 1 over epsilon, and there's a log, but the log contains mu square over m squared. There's no dependence on momentum here. So again, once again, you have mu running of G in low energy, but there is no physical running of G at low energy. So the physical beta function of G really is 0 in this regime. And this becomes clearer if you look at the 4-point function now in terms of the renormalized coupling. In red, you have the tree-level amplitude. It goes like s squared plus t squared plus u squared. And the one-loop corrections all go like either third power of these Mandelstam variables or 4 powers of the Mandelstam variables. There's nothing going like 2 powers of the Mandelstam variable, so there's nothing that you can interpret as a running of G. A running of G will manifest itself in further terms proportional to S squared, T squared, and U squared. Okay, so the physical beta functions in this effective field theory regime for G is 0. For G6 it's also 0. G8 happens to run. This is related to these, to these logs here. You see you have S to the power 4 log S. This gives a beta function for G8. Okay. So these are things that John Donoghue had been saying for a long time in connection with what people do in the FIG. So if you compare these physical beta function that I showed you with the mu beta function, well, the mu beta function is also non-zero, and that's wrong because there's no running at those scale. And the FIG, when you expand it for low energy, it goes like G square and then K4 over M4. So there's a quartic coupling with scale, with momentum. And indeed, when K goes to 0 in the limit, this goes to 0. So this is consistent with the statement that in the effective field theory, the beta of G is 0. Sorry. This thing is true asymptotically. This is what the FIG sees. So this quartic running, which you see in the FIG, you can think of as being a part of the threshold behavior, which is not seen in the effective field theory. Okay, so this is the general form of the amplitude. It's very complicated. It's actually 3 times what you see here because you have to add the terms, the same terms with STU interchanged for crossing symmetry. Now, this contains all the terms with 6 and 8 powers of derivatives here that you have in the low energy effective field theory. And so the typical expectation of somebody doing effective field theory is, oh, it's ugly, it will remain there. This theory ceases to be valid when you reach the first, the mass threshold. But actually, something rather somewhat unexpected happens is that if you go to high energy, meaning above the first, above the mass threshold, all those terms with higher powers of, so terms like S to the 6 or, sorry, S cube or S4, all those terms that we see in the effective field theory at low energy, they just disappear at high energy in the sense that their coefficients cancel. There are complicated cancellations. They're not so easy to see at first sight. At high energy, well, you have to renormalize. Well, if this was the coupling defined in the effective field theory, the high energy coupling is better defined with a finite shift. So this is a finite renormalization. And in terms of this G bar, the amplitude takes this very simple form, the tree level, and then these 3 terms here. And you see that now only terms quadratic in STU appear. So you can, on the basis of this amplitude, define a physical beta function for G now. It makes sense now. And it's just 5G square over 16 pi square. And it agrees with the mu running in this case. And it also agrees with the one loop FIG calculation. So in this regime, actually all definitions agree. If you, here you see, I assume, for example, that the coupling at low energy is 0.01. I just pick some number. The red dashed line gives you the behavior, the asymptotic behavior of the amplitude. This is only to be believed or relied upon in the asymptotic regimes when K goes to 0 or K goes to infinity. Here in the middle, this is just some ugly interpolation. You see, Now, the units here are k over m. The threshold corresponds to k equal to m, so 0.1 here on this scale. This is the threshold for production of the ghost. So what particle physicists always do is they interpolate the low energy and the high energy behavior by some matching. And so if they have some constant coupling here at low energy, they assume that it remains constant all the way up to the threshold. And they match this to the high energy behavior by some offset, which is this little, the offset is just this finite renormalization that I did here, okay? Now, the FRG, on the other hand, gives you a continuous interpolation. So if you start from this value in the infrared, you integrate the RG, and you get some smooth curve, which has the same asymptotic behavior here for large momenta, but it doesn't actually reproduce the offset of the physical amplitude. I haven't checked, but I believe that this is probably a regulator-dependent quantity, this offset, and so it may be possible to choose a regulator for which the offset is also correctly reproduced, but this would then be a scheme-dependent statement. Anyway, you see that. So one important point is that this behavior is clearly not something physical. The point is that you can't define the physical running in the threshold region, because physical running is only defined in the threshold region. The scattering amplitude has a very complicated form, and it cannot be in any way approximated by a single function of a scale. Okay. There's a high energy puzzle that we don't understand. I already mentioned that if G is negative, this theory is asymptotically free in the ultraviolet. And so you say, oh, nice, asymptotic freedom. But you see that this coupling has 4 derivatives. So when you go at high energy, the interaction grows like energy to the power of 4. Now, the fact that the coupling goes like 1 over the logarithm of energy, it is totally swamped by this 4 powers of momentum. And so it's still not clear what is the meaning of asymptotic freedom in this situation. I have to say that this we don't understand. It has been noted recently by Bob Holdom that if you compute inclusive cross-sections in this theory, there are further cancellations between the contributions of the ghosts and the massless particles in such a way that actually the cross-section is well behaved. And this has also been verified by Diego. And it's also true at 1 loop, which is rather remarkable. But then you may ask, why can't we consider just exclusive cross-sections? They would not have these cancellations. So there's room for further work here to understand better what happens. All right, so I think that I can come to my conclusions, which is that the physical running is really only defined in the asymptotic regions, and good news is that FRG does agree with this physical running in the asymptotic regions. In the low energy effective field theory, you don't see running of the low energy coupling. Instead, you see these operators with 6 and 8 derivatives. The power running that you see in the FRG at low and intermediate energies, you can think of as being a part of the threshold behavior where there is no definition of physical running. So it is some mathematical interpolation that you shouldn't attach any physical meaning to. Now, the other good news is that the fact that these dimension 6 and 8 operators go away, they melt somehow at high energy, it shows that there is the possibility of having actually a smooth interpolation between the low energy effective field theory regime and a ultraviolet complete, maybe asymptotically free or maybe asymptotically safe regime. That is still to understand. And perhaps the most surprising lesson for me was that also the mu running is not always physical. Now, this mu running, I tended always to believe, to fully trust in the sense that those beta functions are universal. But even those beta functions sometimes contain some terms which are not related to the behavior of the amplitudes. And it appears that this is the case for the beta functions of high derivative gravity that I showed initially, those that were established already long ago. There are pieces in there that originate from tadpole graphs that don't have dependence on momenta. And so I think that those beta functions have to be corrected too if you want to extract physical information about amplitudes. So this is also ongoing work now. And maybe, yeah. Thank you.